Hi guys, this is my second video on physics, and let's start right away. The first topic is dynamics, and the topics are uh, first uh, equation to horizontal and vertical components and the tension. Okay, yeah. Okay, so first equation. So there's actually only one equation you need to know for dynamic, and that is F equals ma. As simple as that. You know that it's ma and not mv because mv is something different. Mv is momentum, uh, represented by the letter p. So F can also actually be represented as a change in momentum over change in time. Yeah. So force can be represented this way also. So here m is mass. Here m is mass, a is acceleration, and v is velocity. Okay, done. Oh yeah, and one more thing to take note. This f, this f right, is can also be is called like f resultant. Means it's like the resultant. Only you can have many forces acting on an object. Only the resultant force will influence its acceleration. So for example, right? Uh, let's say uh, we have an object moving on a ground, and let's say there's a force of 10 newtons pulling this object in this direction, and let's say this object has a mass of 2 kg. So a so the acceleration is 10 over 2, which is 5 meters per second square. Yeah. Let's say there's another force, a frictional force, acting in the opposite direction, and it has a magnitude of 1 newton. Then the resultant force isn't 10 anymore, but it's 10 minus 1, which is 9. So the acceleration is not 5 meter per second square anymore, but it's actually 9 over 2. Yeah, which is 4.5 meter per second square. Okay, so just take this into account. And let's say um the instead let's say that instead of 1 newton the frictional force is actually 10 newtons or so, then the resultant force zero would be 0, right? Resultant force would be 0, and acceleration would be 0 meter per second square. So that means there's constant velocity. Okay, yeah. Okay, so right, that's all the quantities and that's all the terms and equations here. And note that the ones in gray are just extra things you need to know for dynamics. So the next topic is horizontal and vertical component. And take note, this is a disclaimer. This is not a proper name. It's just the name I gave to this topic to explain what it's about. So it's basically right. Let's say um, let's say you have an object um, moving on a floor, a ground. Okay, so like okay, right. So like this, you have um, you have horizontal, and you have the vertical, yeah, with respect to the object. So right, uh, what I'm saying is that let's say there's a force acting in this direction. Okay, okay. So what I'm saying is that basically, like you look, you know, in vectors, you learn that you can when you add two vectors, you uh, connect connect the ends, right? Connect the you connect the ends, and that's how you add vector. You connect the start of the first vector to the end of the last vector, and that's how you add vectors. However, you can do it the other way, which is basically right. This vector can be made up of two other vectors or forces. So it can be made up of this vector can be split up into these two other vectors, or maybe even these three other vectors. Yeah. So what I'm saying is that so you see this vector, it can be split up in the following way, like into this. Okay, I'll use a different color. Uh, so blue. So it can be split up into, let's say, uh, this vector in the horizontal direction, and this vector in the vertical direction. Okay, and this vector can move over here. Okay, so if you want to know how this, like let's say this is a force acting on the body. So how do you want to find out how this force affects the motion of the object? So it's actually only the horizontal component of this force that will affect the motion of this object. See? And the vertical component will just affect something else. So right, right. It's like the horizontal component of the force will affect the will affect motion of the object, and the vertical component affects um affects something called the normal force. The normal force. Okay. So yeah. So let me explain what's the normal force. Normal force is basically like this. Let's say you have a table. On the table, you have an object. And this object, right, it has a mass, it has a let's say it's on Earth, it'll have a weight, right? It'll have a weight pulling down on the table with a magnitude mg, with m the mass of the object. So the normal force, right, is uh is other is the force that is the force that the table exerts on this object, and we call it, yeah. So this is the normal force. And take note that the normal force is so this normal force has the same magnitude but opposite direction as, like, let's say this weight, the weight direction as the weight force. Okay, so this normal force is what the force that the table exerts on the object to pick it up here, like support the object. So the object is too heavy and the table like cannot exert a strong enough normal force, then it will just break. Okay, so like that. Okay, so let me explain this. So, oh yeah, so one more thing, right? So if you know, like, say this angle here, we call it theta, you can actually calculate, like, and you also know the magnitude of the force here. You can actually calculate the magnitude of the horizontal and vertical component of the force, right? Okay, then just add this here. Do this. Okay, so it's basically right. Uh, basically right. If this is F, then the horizontal component is uh, F. Use your trigo. F sine theta, and vertical component is F cosine theta. So if you want to know the motion, just use F equal use F. You know what? Calculate F sine theta and use F equals ma to find out the acceleration and the vertical component, and then the normal force will basically you don't need to know. So this will affect things like friction, which you don't need to know how to calculate and stuff. And yeah, all right. Let me use a special case to let me use a special case to explain special example to explain this. Um, I'll just flip it like this. So say you have an object on a slope. Oh my god, never mind. Let's do this. Okay, something like this. Okay, so say you have this object on a slope and there's a weight, right? Um, so this is the direction of the weight and it has a magnitude uh, mg. I'll just write it here. So in fact you can just split this. In fact, you can use the concept of horizontal and vertical component to split it into the different components. So here, like horizontal is with respect to the object is here, vertical is like this. So basically, you can split up into these two components like this. Yeah. Okay. Yeah, like this. So this is mg. So if you want to find out the magnitude of like, so okay, wait, this, so this force, you can move it here, and this is what will affect the motion of the block. So assuming there's no frictional force, this block will just slide downward with this force, and this force you can also move it here, yeah, and this is the normal force, this part here. So if you want, to calculate the magnitude of the horizontal and of these two forces, you need to use you firstly you need to know this angle here. This angle here is, that's called theta again. So if you use similar triangles, right, you will find out that this angle theta here is equal to the angle here, and so this is also angle theta, this mg. So the force here is, you use trigo. Normal force is mg cosine theta, and this part is mg sine theta. Okay, so these are the magnitudes of the two forces. Yeah, and let's say this block is not moving, it basically means that friction has the same magnitude as mg sine theta, as this force, which is mg sine theta. Okay, so let's say there's no friction or air resistance or whatever, then you can just use F equals ma, and you find out the acceleration is uh, uh, which is F over m. The force is mg sine theta, and you find the acceleration is v sine theta. By the way, this is actually, from this you can actually tell that the acceleration is independent of the mass of the object on the slope. Okay, so that's this part done. Okay, so now I'm going to move on to uh, tension. Okay, so what is tension? So let me use this example to explain. So imagine you have a ceiling, you have a string, okay, you have a string hanging from the wall, and this object is attached to the string. Okay, so uh right, so this object has a mass. And therefore, let's say it's on Earth, it has a weight. So you'll have a weight of, mg. Okay, This is the force that's pulling the string. What tension is force. So by Newton's third law, every force must have an equal and opposite force. So tension is another force the that the string acts on the ball to make sure it doesn't fall. So this is tension. So this is tension. Okay, so tension is basically like the force that the string acts on the object to make sure it doesn't fall. Okay, so in this case, the tension is basically just um uh mg. It's basically just mg. Okay, okay. Um, okay. So basically just mg. So when does the string break? So it's basically right when the object is too heavy, the string will break, right? So this is because like the tension the tension that the object has exerted on the string is too high, and the string cannot provide enough tension to balance the force. So it's like E max is already greater than the weight of the ball. Okay, so this is the concept of tension. So alright, let me just talk about a question in the common test that appear in the common test. So here's a picture. Here is here are two strings, and the question says um actually the question says there are two tension forces acting on these two strings, T and T, T and T, and these are two strings. This is a picture, and there's a weight acting downward. There, here's the weight of the picture. It's acting downward. Okay. So question asks you to express the weight in terms of the tension of the string. So it's basically right. The weight will exert, right. So it's basically right. The weight will You can move the weight vector around. It is supposed to originate from the center of this object, but you can move it around anywhere. So let's just a diagram here. So this is the weight, and you can move the vectors around all you want. Like this. Okay, like this. Yeah. So these are the two tension forces. And the question also mentions the angle here. Yeah. So it's basically right. Because the whole thing is in equilibriums, right? So they form the three vectors form this closed triangle, and yeah, so you can say that's it. So it's basically tension is so the weight will let's see. So basically, right, you have tension is basically acting to support the weight. So weight is actually like in the opposite direction like this. So from here, either from here you can just calculate use vertical and horizontal component to calculate the tension and stuff. Like sine theta is like here the weight is a vertical component. So here's sine theta, here's sine theta, add together as 2 sine theta, t sine theta. And then, or either you can just do it here. Yeah. So this is t sine theta, and add together is 2 sine theta. Okay. Okay, so next I'll be moving on to the next topic, work, energy, and power. Okay. So basically what I'll be talking about, the three topics are basically just simply work, energy, power. Okay, that's all. Okay. So first, work. So work is basically like this. W equals Fd, or force times distance. Work equals force times distance, as simple as that. So what it means is, like, let's say, okay, so let's say there's a ground and you have an object moving on the ground, and this. So let's say there's a wait, let me put here. So here's an object, and let's say someone is pulling this object with a force of 23 newtons. 23 newtons. He pulls it for 3 meters. Okay, so here the work done by this guy will be 23 times 3, which is uh, equal to 69. Okay, 69. So let me ask you a question. What is the unit of this 69? So the answer is 69. The unit is actually joules. Okay, joules. So actually you can kind of the derive. So if you really, assuming you really don't know its joules, you can kind of derive it in a way. So it's like 23 here is 23. The unit is newtons. The unit of force is newtons, and the distance is, the unit is meters. So in a way, you can also say basically this work, the 69, is 69 newton meters. You can also say it this way. So you can say like joules is actually newton meters. Newton meters. Just like say watts is joules per second. You can express it this way. Okay? And just to sidetracking a bit. So you know F equals ma, right? What is the so in fact you can express all the all the derived unit in terms of SI unit. So for example, um, F is Newton, M is kg, and A is meter per second square. So Newton, Newton is, you can say it is you can say Newton, okay, not so small. So you can actually say Newton is kg meter second second square. Oh god, what? Okay, so Newton is kg meter second per second square, and you can also say and joules is Newton meters, right? So it's equal to kg meter square per second square. Uh, yeah, like this. Okay, like this. And also, so um, and yes, and also, okay. So let me erase this one first. Okay, so just one more thing before we move on to energy. So right, so work, the units is joules, and energy units is also joules. So in a way you can say work done is equal to energy. Work is equal to energy. It's sort of like work energy equivalent. So let's say in this example of someone exerting doing work on an object by pulling it this far. So here we can just say uh, work done equals the kinetic energy gained by the object. Okay. So assuming there's no friction or whatever, this is the case. Okay. So let's say you have an object in free fall. So this is this is the weight of the object, um, which is a force, uh, yeah, mg, with a magnitude of mg. So here, done equals GPE lost by GP lost by this object, which is equal to the KE gained by this object. Okay, work done equals the gravitational potential equals to the KE gained. Okay, work done by this object. So now let's move on to energy. Okay, so here we have the term where I've added the term and equation. So take note, I'm just only adding the new terms and equations and not the old one, otherwise there'll be too many. So I'm moving on to energy now. First, uh, gravitational potential energy. Maybe bigger. Okay, it should be big enough. Okay, so gravitational energy, the formula is mgh. M being the mass, G being the gravity, and H being the height. So it's basically right like this. You can derive it this way. So you have an object at this height, yeah, at this height, and you let it fall to this height. Yeah, so this is the object after falling for a certain height. After falling for a certain height h. Okay, so what is the work done by the, so first we know that the work done, first first we know that GPE, that's lost by the ball, is equal to the work done, which is equal to um, the force times the distance, which is equal to, use F equals ma times the distance, mat, and this is equal to, so you notice here, right, that A is basically the acceleration due to gravity, which is d, and d is basically h. So dp equals mgh, and we put as a side note here. And g equals h. And this. Okay. This is how you derive dp. Okay. Okay. So that's gravitational potential energy explained. Now move on to uh KE. And the formula for KE is half mv squared. Okay, this. So how do you derive it? So basically, right, let's say you have this object. Um, let's say you have this object, and you do work on it in a certain direction. Let's say this direction. You do work on it. So we use the formula for work done. It's like this. So um, so here we need to use the formula v square equals u square plus 2as. Okay, but so for the first case, let's just assume that the object is not moving and you do work on it like this. Okay, so you have work done equals force times this distance, force times distance, which is equal to ma times the distance is equal to m half m 2as. And note here that we are assuming it's one direction, so the displacement and distance are the same. Okay, so like this you have so squares is v squared, so the work done is half mv square, like this. So now let's assume is initial velocity v squared equals u squared plus 2as. So then we have w equals 4 times distance equals oh yeah, wait, let me add something. So we're assuming that originally there's an initial velocity, so it already has a bit of ke, which is half mu square plus the force extra work done. So basically half mu square plus mad equals half mu plus half m 2as. Here distance and displacement are the same, so it's equal to half m u square plus 2as, which is equal to half m v square. Okay, like this. Okay, so that's energy explained, and this is the formula. Okay, so I've added the term and equation. So now I'll be moving on to power. So basically power represented by capital P equal to work done over time and or also energy over time. Okay, like this. And so let me add it here first. Yeah, so there's actually another equation for power. That is P equals FV. Wait. I did. Okay. 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 Yeah. So there's actually another formula for power, which is wait. P equals F V. Here F is the force and V is the velocity. Why is this so? So it's basically like, right, P equals work done over time. It's equal to force Fd over time, and it's equal to Fv. So here x, we have v distance over time equals the speed or the velocity. So this is because acceleration, the power is like for a fixed point in time, so acceleration is not taken into account. So you don't have things like half u plus v. So this is another equation for power. Let me add it here. So there's one more equation, or so-called equation that I would like to talk about, which is efficiency. Okay. So efficiency is what is it? Efficiency is equal to the energy output over the energy input times 100%, and it's also equal to power output over power in times 100%. Okay, so I'll just put this here like this. And that's all for this video. Thank you for watching, and bye bye.